Hey, Mr. Sams. You got the breakfast of champions, I can tell.
Coffee and cookies.
Cookies. Cookies is the breakfast of champions.
I made these with my kids the other day.
Nice.
Yeah.
That's very cool. You could make those things with your kids. They got raisins in it. Actually, that's well, I got something healthy in there.
Oatmeal raisin cookie, man.
Raisins. There you go.
You don't want to know how much butter's in these, though.
A lot, I bet. Yeah, okay. Okay, so today, folks, we want to just do some more stoichiometric problems. Problems with stoichiometry.
Yeah, that was a mouthful.
Yeah, well, you're trying to, yeah. So, first of all, I think before we do that, should we do a little cool experiment?
Let's do that.
So let's burn some propane. What do you think?
I'm always up for burning stuff.
Let's burn in the morning. You know, it is 5 degrees outside.
It's stinking cold this morning. It took me 15 minutes to scrape all the ice off my car.
Yeah, you should get a garage. Yeah.
Yeah, I used to have one. Now,
Yeah.
now it's a bedroom for my
Yeah.
children.
Okay, it was 5 degrees this morning here at Woodland Park. Hey, let's do that demo.
Okay.
Alright, I got my propane torch here today, and what we're going to do is we're going to burn a little bit of this propane, and then we're going to use some stoichiometry, and we're going to figure out how much carbon dioxide I produced in this reaction. So in order to figure out how much propane I burned, I need to weigh my torch first. Okay, so put it on here. Looks like it's 286.5 grams. Alright, now I'm going to turn this on. And hopefully I can get it lit as soon as the gas turns on, otherwise, there we go. Otherwise the mass that went down wasn't going to be that was burning. So, we'll crank it up a bit. Ah, yes.
So what's happening to the mass of the gas in the torch now?
Well, the mass in the container is going down because it's obviously coming out and burning. It's reacting with the oxygen in the air. It's producing water vapor and carbon dioxide gas. We want to figure out how much carbon dioxide we're producing. All right, so let this burn for a few more seconds. And we'll reweigh it. Two 85.2 grams.
So what do we do
so
now?
if we just subtract the masses, then we can get the mass of propane that was burned. So we burned 1.3 grams of propane in that process. So we can go do some stoichiometry now and figure out how many grams of carbon dioxide we produced.
Let's do that.
I like fire.
That was cool. Well, let's actually do the problem here.
Okay, let's work it out.
Okay, now what's the first thing we always have to start with, Mr. Sams?
We definitely have to have a balanced
Oh,
equation
yeah,
first.
yeah. Well, so you had that propane in the tank. So that's C3H8. And we react that with
Oxygen in the air.
Oxygen in the air. And that's O.
It's just O2.
Oh, yeah, man, that's one of those Brinkelhoffs, Magic Sevens. And of course, that produces two things. What?
Oh, my mouthful.
Well, I'll tell them, Marty. Carbon dioxide combustion reactions always produce the same two things: carbon dioxide and water. Okay, so we got a balanced equation. We're good.
Yeah, we will.
Do we have a balanced equation? Oh, we got to balance it.
Yeah.
Hey, it's the CHO2 rule, remember? CHO2. All right, so I got to put a 3 here. Do carbons first. Hydrogen, I got 8 hydrogens, so I'm going to put a 4 there. Now what do I do?
Count our oxygens on the right. So
I got 6 here.
And 4.
And 4. That's
10.
So it's a 5 here.
Yep.
Okay, we're good. So now what do? We write down?
Write down what we know.
Yeah.
And put it underneath the thing that we know. 1.3 grams of propane.
What are you trying to find?
We're
Grams?
trying to find question mark grams of CO2.
So how many grams? So it's a gram to gram problem.
It
So
is.
I think we should use our
Mole map.
mole map. Okay, let's go to our mole map. So
The
we're going,
land of the mole.
you rock, Mr. Sam.
I know.
So we're going from grams to grams. So to go from grams to grams, you go through the molar mass. And then you go through the mole ratio, and then you have to go through the
Molar mass again.
But it's not the same molar mass
Nope.
because it's a different chemical.
Other substance.
All right, let's start with what we know.
All right.
All right, 1.3 grams of C3H8. Hey, folks, one thing I want to just very emphasize,
Very emphasized.
something
That's
like
nice.
that, is I want you to emphasize. You must write this down, guys. If you are not copying the examples down, working this out with your calculator, then you're going to just hurt yourself.
Yes, practice.
Practice makes perfect. All right, so we want to go to the perfect practice. Okay,
perfect.
is that we want to go through the molar mass here, right? So the molar mass of C3H8, we're going to say grams of C3H8 in 1 mole of C3H8. Okay, to do this now, what we need to do is we need to figure out what is the molar mass of C3H8. So on my calculator, there are P3? What
There's
normal?
that P.
There's 3 times 12. The weight of carbon is 12 plus
8
plus
times
8.
1.
I
Yeah.
want to say 8, yeah.
Yeah.
And that gives us a molar mass of 44 grams. All right? So now what do we need to do is we need to then go from moles to moles. So we're going to use the mole to mole ratio, and that's from the coefficients in the balanced equation. But since I have moles of C3H8, I'm going to put moles of C3H8 on the bottom, and then moles of carbon dioxide on the top. Now, Mr. Sams, where do we get that?
What? My torch?
Oh, you
I
have
got
your
at the
torch.
hardware store.
Nice. Yeah, but I wasn't asking about that. I said,
Oh.
where do we get the coefficients?
Oh, you get those from the balanced equation?
Yeah, and you see there's a 1 there, right? And here we have a 3, so we put a 3. Mr. Sims, what are you doing?
Playing a fire.
I can tell that. Okay, cool. Hey, keep on doing that if you want, but don't point it in my direction. That would be a safety hazard without our safety glasses on.
Exactly why it's pointing that direction.
Very good call.
Yeah, I can
Okay,
warm up my coffee.
now we want to do is we want to go from moles to grams, okay? And to go from moles to grams, these right here have canceled, right? Actually, by the way, these have canceled as well. So I have moles of CO2, so I'm going to put moles of CO2 on the bottom and grams of CO2 on the top. And then to do that, we are going to say there's 1 mole is the number of grams of carbon dioxide. And the carbon dioxide, that's just 1 carbon, so 12 plus 2 for 2 oxygens times 16. And that, of course, is 44.
Whoa.
Whoa, that doesn't happen very often. That the
No.
2 chemicals have the same molar mass. Now, that's odd, actually. So, how am I going to solve that problem? Well, I'll say numbers on the top are times 1.3 divided by 44 times 3 times 44, which is actually just going to be...
You could have even canceled the 44.
Yeah,
if
you really could
wanted
have.
to.
Yeah, that's not going to happen very often, guys. That's 3.9 grams of carbon dioxide. So from that experiment, when you were burning the propane deal, you produced 3.9 grams of carbon dioxide.
Yes, I did.
Contributed to the global warming problem, I guess, or whatever.
I suppose so.
Yeah, there you go. Okay. Okay, that's cool. Hey, let's look at another clip of sodium and water, and then we'll
Yeah.
do a demo.
Let's do
yeah.
it.
Now it's my turn to
This
play.
is fun.
Well, today what we want to do is cut you. No. I want to cut a piece of sodium. This right here is sodium metal. It's actually very, very dangerous. It's immersed in oil because otherwise it really is very, very reactive. And so I'm going to cut this. Sodium is a metal. So watch me cut this here. I'm going to cut a chunk of sodium. If you look at this as I cut it, if you look and zoom in there, you can see the silvery nature of this. It eventually is going to change because it's oxidizing right here. Now this little piece right here, actually that's a big piece, we're going to react away. But first of all, before we do that, we're going to find out what its mass is. So we're going to take this piece right here, and we're going to take it and put it on the scale. First of all, my scale has a petri dish on it. I'm going to push the 0 button. I just put the off button, so we won't do that.
That's the evaporating dish, by the way.
Is that an evaporating dish?
It
That's
is.
right. It's an evaporating dish. I knew that. And let it 0 out, and I'm going to push the piece of sodium on there. And so, wow, we have 1.64 grams of sodium.
Do you really want to use that much?
It'll be all right.
Okay.
We'll stand back though. And then we're going to react it in just a container filled with water, and then we're going to predict how many liters of hydrogen gas it'll produce at STP. Cut. One consequence of putting the sodium into the water is that it will produce hydrogen gas, which in this reaction is highly exothermic. So in theory, it will ignite the sodium gas and we'll have a explosion. Okay, I'm going to drop this and kind of get out of the way. Mr. Sams, will. You can see the hydrogen gas being produced. And if you get a fire right there, it might blow up, but it's producing that hydrogen gas. You can see the gas being given off in the container. I've blown up beakers doing this and all kinds of things. But you can see the gas, and as that gas is given off, we're trying to predict how many grams or many liters of gas are coming off from our 1.65 grams. Mr. Sands, I bet you could zoom in.
Oh, I'm zooming.
Oh, okay. Now see how it kind of rocks across there? That's kind of cool how it does that. It's just walking across the deal there. getting very hot. If that had been hot water, it would have ignited right away. It looks like it's not going to. Wow. Did I ever tell this story about my my science teacher who took a big chunk of sodium? No, I better not tell you that story. Anyways, it was not a good thing. Lots of trouble. All right, so again, you can see the idea is that there's hydrogen gas given off, and we're going to predict now how much hydrogen gas came. Yeah, okay. So we had 1.65 grams of sodium that reacted. It's kind of a bummer it didn't explode, but well.
Sometimes it does. It's kind of old.
So first thing we need to do is write a balanced reaction.
That's
sodium
really a good idea.
is Na plus water.
Let's call it HOH.
Yeah, it's a lot easier if you look at it as HOH here, guys. This is a what type of reaction?
That's a single replacement reaction.
See, the sodium is going to react with the hydroxide. You could look at the table to see if activity series, if it's going to react, but we don't really need to do that because, well, we saw it react.
Yeah.
So the sodium is going to get together. He's competing with the hydrogen for the girl, as we like to say. So you're going to make NaOH. Now, the reason I know it's NaOH, pardon me, is Na has a charge of +1 and hydroxide is -1. You still have to play the charge game when you're building this product right here, but it is 1 and 1, so it cancels out. Plus hydrogen. Now, watch this. Hydrogen has a 2 in it because, of course, it's H2. It's one of the Brinkelhoffs. Is that a balanced equation, Mr. Sam?
It is not.
I don't believe so. I've got 2 hydrogens. Actually, when you think of the hydroxide, think of the hydroxide as 1 unit, and the hydrogen gas kind of related to this. So if I put a 2 right here, that's like 2 hydrogens. That was canceled for that.
Yeah, but then there's 2 hydroxides.
Then that gives me 2 hydroxides. So I have to put a 2 there.
Yep, and then that's 2
and that
sodiums.
messes up and gives me 2 sodiums. There you
it
go.
is. Perfect.
Now, so what did I have? Write down what I know.
1.65
grams of sodium. And the question was here, how many liters of hydrogen gas are formed at STP?
Yep.
Now we live here in Woodland Park, Colorado, and it is never at STP.
No, it's pretty close to the standard temperature today.
Yeah, that's true. Yeah, but not
Actually,
just
it's colder than standard temperature today.
Yes, definitely. But we're going to pretend that we were at sea level on a cold day.
Okay.
Okay, so let's start with what we know is a fraction over 1. Actually, let's look at the mole map.
All right.
Yeah,
Let's
okay.
do that.
So we're going to go from grams to liters
liters
down there. So we just have this fraction, this fraction, and this fraction to deal with, okay?
All right. Molar mass, mole ratio, 22.4. Let's
So
do it.
1.65 grams of sodium over 1.
Okay, so the molar mass of sodium, you look on the periodic table.
Grams Na to 1 mole Na. This one we don't have to do any kind of math. We just look on the periodic table.
Yeah, it's
and
23.
this is 23. Is it 23 point something? So on the periodic table,
Yeah, it's
that's
23.
23.0. You
Yep.
want to go to the nearest decimal, but it's 20.30. Yeah. So now we want to go to mole to mole, right?
Yep.
And so I can say moles of Na. The grams of Na cancel here. The moles of Na, and then the
And we're going
moles
to
of
hydrogen.
hydrogen. And there's 2 moles of sodium. That's from the 2 in the balanced equation, and 1 mole of hydrogen. There's no number in front, but of course that number would be a 1. Now the moles of sodium cancel, and now we want to go one more step, and we can say 1 mole of hydrogen. Now where would we go?
We're going to liters, so we're going to
So-
use that 22.4
So
thing.
there's 22.4 liters of hydrogen there. And now we've got it done. Now we just have to simply put the times ones on top and the divides on the bottom. So let's turn my calculator on. And I can say 1.65 divided by 23 divided by 2 times 22.4. That's my answer.
There it
and I
is.
get, we produced 0.8, probably 3
3 sig
digits,
figs, 803
0.03 liters of hydrogen gas. That was not too hard, is it?
No.
So that's how much we produced while
Yep.
that thing was fizzing.
Yeah, so that's, I don't know, it's probably roughly the volume of my coffee mug here. Maybe not. This is probably a little less than that.
Yeah, but something like that.
right around here.
So if we could have collected it somehow,
Yeah.
although that would have been dangerous.
Well,
So we didn't
That would
do
have been
that.
kind of fun, though. Could have lit it on fire and turned it back into water.
Yeah, that would have been cool. Okay. Well, now we don't have any other cool demos, but we are going to just do some more examples for you, so you make sure you get some
And
ideas.
I may disappear because I have to go teach class here in a few minutes. So
Oh.
if you see me just magically disappear, that's where
It's
I'm
because Mr. Bergman's going to be on Carl then. Okay. So let's go ahead. Here, I've given you a balanced equation. This is a little easier almost. Start with a balanced equation. Guess what? You're
going. Hey, it's already there.
We're going to recopy it though.
Okay,
'cause
you give us some room to work with.
2KClO3, yeah. Turns into 2 KCl's plus 3 oxygen. So if we have 5.67 liters of oxygen,
We're going to assume STP here, by the way.
at STP, so this would be at STP, It says how many molecules of KCl. That's really not molecules.
Yeah, not really molecule. Formula units is really the correct
Yeah.
term for that. But yeah, let's
Let's
just
just
figure
say
out how many of them.
particles. We'll call it
Yeah.
particles.
Yeah.
So how many particles? So we're going from here to here. Now that's going from a product to a product. Is that legal?
That is, you
It
can
doesn't
go
matter.
anywhere to anywhere from anywhere in a balanced equation. Does
Yeah.
not matter.
All right, so we'll write down what we know as a fraction over 1. Notice one thing I'm doing, 5.67 liters of O2. I do
Yep.
not just write 5.67. I also do not just write 5.67 liters. I write 5.67 liters O2.
Yes. Tell us what you have and how much you have of it.
No naked numbers. A
No,
number
not
must have a
even partially
unit
naked ones.
and a chemical. All right.
Yes.
So then I'm going to say...
We're talking full Victorian garb here, covered neck to
Nice.
ankle.
Hey.
No showing wrists.
My students, they don't do that.
No showing ankles.
In the summer, you just can. They don't wear enough at all. Yeah, I don't
Yeah,
know. Okay, I'll bet you do that. All right. Where am I at? Liters of oxygen to moles of oxygen. So I'm going to say 1 mole is 22.4 liters. Liters of oxygen cancel. Now I'm going to do the mole thing, right? I didn't show you the mole map, but I think we're getting advanced
Yeah.
enough. We don't need that. So mole to mole, I'm going to say moles of oxygen on the bottom because, of course, the moles of oxygen are on the top in the previous problem, and go to moles of potassium
Yep.
chloride. And that's because, yeah, so this will be a 2 and this is a 3 from the balanced equation. Moles O2 cancel, and I have one more step to go, right? And what I'm going to do, I'm going to say moles of KCl to grams of
Nope.
KCl.
We're going particles.
Oh, no, oh yeah, to particles of KCl. I'll call it P.
Perfect.
Actually, part.
Part it is.
And then this will be 6.02 times 10 to the 23rd.
Yeah, anytime you go to particles, you use 6.02 times
Now remember,
10
a
to the 23rd.
particle, I think there's some confusion. A particle is either an atom or a molecule,
Or in this case,
or sometimes there's another thing. We haven't really talked about this,
Yeah.
but it's also called a formula unit.
yeah, what that is basically like a molecule of an ionic compound. Ionic compounds don't really form individual molecules,
Yeah.
but they form the lowest ratio of the ions, and that's we're going to treat it the same way in stoichiometry, and we'll talk more about that in later units.
So 5.67 divided by 22.4 times 2 divided by 3 times 6.02. Now just a reminder, when you type in the 6.02, you must use the double E button, 23.
Do not use times and 10.
Messes you up big time, fellas. It
Ever.
actually makes it 10 times bigger if you think about it.
Yes.
Or then sometimes it flips the...
And sometimes if it's in the denominator and you don't use
messes
parentheses, it's a
everything
mess.
up.
That's why you use the E button. I don't care what your math
So
teacher
1.02
use the E button.
times 10 to the 23rd
E button.
particles
I am your father.
of KCl. Mr. Sams, you've become the Darth Man.
I think my coffee just kicked in.
That must be it. Yeah, okay, cool. Hey, and I think we're going to do one more example, maybe two. Let's see how this one goes. Of course, we always start with a...
Balanced equation.
Yeah, we're getting a lot of space on this one, so this will be interesting. Okay, so we've got molecules of... All right.
Oh,
Guess what? Same reaction.
it's the same reaction.
All right, well, if molecules of oxygen gas is formed, so when it says it's formed, that makes it a product. So oxygen gas is formed, O2, from the decomposition of potassium chlorate. Now, by the way, let's just go ahead and figure that out.
Yeah.
Potassium is K positive, and chlorate is ClO3 negative 1. Oh, those balance out.
Hey,
That's pretty
that's
easy.
convenient.
So that's KClO3, breaks into oxygen, and it says potassium chloride. Chloride is Cl negative 1, so Cl negative 1 and potassium positive also cancels out, so it's KCl. This is the same reaction we just
It
saw.
is.
And so this is a 2, 3, 2. I think I might have rearranged it, but it's not a big deal. How many grams of potassium chloride, so it's asking about this, are formed from what?
2.3 times 10 to the 23rd molecules of oxygen.
So we have 2.3 times 10 to the 23rd molecules, and that's illegal to call that a molecule because
Yeah.
oxygen is nonmetal. So, all right, so I'm going to start with what I know, 2.3 times 10 to the 23rd molecules O2 over 1. Okay, and then I'm going to say 6.02 times 10 to the 23rd molecules O2 to 1 mole O2. Everybody seeing that? I want to get the molecules of oxygen to cancel. Now what's the next step?
Now we got the mole ratio step.
So it's 2 to 3.
Yep.
But I'm going to
Oxygen goes in the bottom.
3 moles of oxygen to 2 moles
Potassium
of
chlorate.
KClO3.
Hey guys, remember when we were all picky about chlorates, chloride, all that stuff?
Yeah.
And you're like, oh, what difference does it make? This is the difference that it makes. They're two
Good
different
point.
substances in the same reaction, so do not get them confused.
Now I want to go to grams, so I'm going to say moles of KClO3 to grams.
Do you know the mass of that?
I do.
Wait. I think I remember.
KClO3.
Is it 122?
It's 122.5, but yeah, pretty good, Mr. Simmons.
Yeah.
But just for fun, it's going to be 39, that's the mass of potassium, plus 35.5, the mass of the chlorine, plus 16 times 3, and of course that's what?
Look at that. I'm
120.
becoming a real chemistry teacher.
Mr. Sims,
I
you
know
are
the molar
amazing.
mass of potassium chlorate almost.
So now I'm going to type it in, 2.3 EE! Did I say that good?
Wow, that scared me. I just
23.
about jumped.
I know. You were pretty... they saw that on the video. You didn't jump at all. 6.02
Oh, that's right, we have a camera. Hi, guys.
EE!
That wasn't quite as obnoxious
23.
as the first. Oh, you missed.
I missed. How do I back that up?
Delete button. Right there.
Delete. All right.
Okay. What was that again?
EE!
There we go. Thank you.
23 times 2 divided by 3 times 122.5 gives me a grand figure of 31.2 grams of KClO3.
So, if I wanted to produce that many molecules of oxygen, I would weigh out 31.2 grams of KClO3, and I'd heat it up, and I would get it.
You were good. Yeah, actually, we didn't put one thing here. This reaction is a heated up, so you put a little triangle there. Okay?
I think we're done.
I think that's it. So, hey, that's how you do these
I
problems.
didn't
You
have to
need
disappear.
lots and lots and lots of practice.
And you will get lots and lots and lots of practice in class.
And so